Hello of the solution of day 19 from Advent of Code. The solution is a little bit complex and we are very interested in the solution, and my colleague Maciek is also interested in the solution. So we both now follow Frank in his description. Please, Frank, what is the solution?
Hello, Thomas. Hello, Thomas. Thank you for the warm words. So yeah, here I want to try to explain day 19 puzzle of Advent of Code. It's called Not Enough Minerals. So what we got here is an input of basically some scenarios, which are called blueprints here. And in each scenario, we got a description of costs of so-called robots. So we got 4 types of robots, which are able to collect 4 types of tokens. So they are called ore, clay, obsidian, and geode. So I call them further on 0, 1, 2, and 3. It's simpler. Okay. So the main point is here, if we want to buy such an Ori robot, then we have to pay for Ori. And if we want to buy a clay robot, we have to pay 2 Ori, and obsidian 3 Ori, and 14 clay, and so on. Yes. So each of the scenario has 4 such rules with the prices for these robots. And then these robots, once bought, they create one of this token every minute. Yeah. So this Ori robot creates 1 Ori in every minute. And the whole simulation should run for 24 minutes. It's here in the text. So yes. Now what we have to do is to find a way to buy these robots in a clever way to maximize the outcome of geode in this case, because this geode is given in the question here down below somewhere. So what is the maximum thing? I will scroll down for it. It's a bit clumsy here. What do you get if you add up the quality levels? And the quality levels are the IDs multiplied by the maximum thing. So the maximum outcome of geode is what we search for in each scenario. So now how can we tackle this? It's more or less simple if we view this as a tree. And the tree has kind of a state. So in each position where we are in our search, we got a number of robots of each type, which are 4 different types. Then we got some tokens collected, which are also 4 things, which are 8 numbers. And then we got the time that passed by, which is the 9th number. So the whole state of such a search is fully described by these 9 numbers. And then we can build an kind of a tree from it. Okay. So we start at the beginning. So this beginning is definite here somewhere. We start with 1 Ori robot, and then this Ori robot begins to produce Ori. And then if we got some Ori, we can buy more robots. And the question is in which order we buy other robots and so on. So if we put this starting state in our root of the tree, then we can create such a node 1. And this node 1 then would be like in the first minutes buy nothing, just wait 1 minute and then have 1 clay. So the state of the collected items changes. Or we can create a state 2 if we can buy something with what we collected before, then we can buy, say, another Ori robot, and then the number of Ori robot increases, but the number of items we have decreases, and so we get a new state. And so we can create from each state all possible states, and all possible following states are at most 5 of them, because we can buy nothing or one of the 4 robots. Yes. So at several states, we cannot go into the next state, for example, because we do not have enough clay or so, then this state 3 is no following state, like here drawn with the 1 and 6 and 7. Here from the 1, only 2 of them are reachable. So now if you think about this tree and this state, so for each of these 9 numbers, we have 24 possible values, 0 to 24. Yes. At most. So this gives 24 power of 9 possible nodes in this tree, and this is a very big number. Yes. So if we really want to iterate all of them, it won't work. So if you try it, you will probably after 10 minutes see your screen and see this won't work.
But some input for you. It just 1 minute. In 1 minute we got heap space error. It's very fast.
Yeah, it depends on how much memory you have and so on. But sooner or later you will recognize this does not work.
Yes.
So, but there are several things we can optimize in our tree. So actually, there are several states which are not reachable. For example, having very much of very expensive robots will never be reached. So if we only traverse the existing states, then it's much less than the theoretical maximum. But still, it's still much too much. Even 24 to the 4th power would be a lot, and to the 5th or 6th power would be too much. So what we can do if we want to traverse this tree, we need to find some kind of optimizations to sort out states preferred early where we know this does not go to a solution. So if we got from this 0 state only 1 instead of 5, then our solution space will be divided by 5. And same as the next. Whenever we can sort out here something more or less early, then it will shrink. And actually, it turns out the whole puzzle is only about finding such observations, which makes it faster. And if you did found enough of these observations, then it will run fairly fast. And now I will present 4 of these optimizations, and then we see that it actually runs fine. So to say here, in the first star, it's 24 minutes. And actually in the second star, the only difference to the first star, this goes up to 32 minutes. So you simply have to find some more optimizations prior to the first star.
Okay.
So I go directly into the second star solution because the second star solution also works for the first star very well. So
long story short.
So there's one optimization we can do. This is we got this factory, and in this factory you got some remaining time. Say you are in minute 20 and you know it runs only 24 minutes, and then you got 4 minutes left. So if you take the highest price from your list of prices, and I scroll this up, for example, here, the highest price of Ori is 4. So if 4 minutes left, then you know you cannot spend more than 16 Oris ever. So if you ever got a node in your tree where you create more than 16 Oris, you know this is not useful because you cannot spend them at any time. So this simple optimization makes it much quicker. So, and then second optimization is the cannot buy anything branch. This is if you buy nothing in in 1 minute and then consider the next minute. It is never useful to buy something a minute later if you would have been able to buy it 1 minute before.
Yes.
So if you buy nothing, you can give like a bit mask, you can tell the next step which of these 4 Oris are not useful to buy. And alone, these 2 optimizations allow you to get a first star in like 5 seconds. So at least if implemented in C++, I run it once here for the records.
4 seconds.
So I implemented these 2 optimizations, and then it's more or less fast. So, and then we have to think a bit more about what can we do here in optimizations. So it's kind of slow here because of the video.
How many nodes or leaves do you got in your tree?
I'm not so sure. So it runs in 4 seconds here, or like 4 seconds. Currently runs a bit slower because of the video creation. So I don't know, it's some million, like 3 or 4 million, something like this.
Okay.
So from these quadrillions of nodes, only some millions are left. And then, okay, here with video, it needs 16 seconds. So now let's look at the other optimizations I actually not found. I did read about them in the Reddit. In the original problem, I was not able to find them. So a third optimizations is for each robot type, there is a maximum cost in this list. And it does never make sense to create more robots of this type than these maximum costs are given. So you know you can spend this not too much, and then you got only the time left, and this sorts out some more of these tree branches. And then there's a fourth optimization, which is a bit tricky to understand or to prove that it actually works, but it shows that if it's possible to create a GOD robot, which is the last one in the list, then it's always optimal to create one.
Yes.
And this actually, again, makes it a factor 100 faster.
Okay, because all other trees or other leaves are not necessary.
Yeah, well, it's simply how early you can jump out and how much nodes this tree in the end has. So I implemented DFS, which means I go into the deep first and then I go back and I traverse the whole tree, and afterwards, so on each leaf I can count how many GODs I collected, and it's my answer. And when I traverse really every node I found, then I have the maximum answer found. And so this works if it's not too much nodes. So with these optimizations, the tree is like more or less small, so small that I can run it in a reasonable time. So cool. I will run it here, so it will also run in some seconds like the one before. And this is actually the solution. So if one has fun with this here in the Reddit, there are much more optimizations described what one can do, and then it actually gives this thing. Some of these Rust people made it run in milliseconds with more optimizations. So if one is clever. And so the thing about this riddle is usually we got these correct solutions and things. So we calculate something and then we need to find the right number, and then that is it. But in this riddle, it was a bit otherwise, because it reminds more of these heuristic problems like traveling salesman and so on.
Yes.
So it's not that we see you actually need the perfect solution, but we just need to optimize our solution to a certain degree, and then it's good enough, and we can find a solution with it. And this reminded a lot of these heuristic problems. Yeah, well.
For me, it was a very great riddle, because at day 19 they combine the searching through the tree and parsing something, and every riddle from the past were now mixed into one big riddle. It was very cool. Not just parsing something, but just find something about a heuristic. It was very cool, and I did not solve it yet. I got too less memory. It was a wrong solution.
Yeah, well, too less. So, by the way, if you get too less memory, you did a BFS. It's a breadth first search. So you go in the tree with a 0, then you create these 5 states, put them on kind of a queue or list something.
Yeah.
Then you take the first from the list and create the next 2, then the second from the list, create the next 5, and so on. What you can also do is not put them on the thing, but instead jump recursive into a function. So with this jump recursive, you don't need much memory.
Yeah,
so
that's right.
Because I choose DFS, which needs actually nearly no, because it's only 32 recursions. It's like nothing, but it does not help much in the end. If it's too much tree nodes, then still it does not work, because it runs simply too long. So, but at least the memory is solved with this. Yeah.
Frank, big thank you. Maciek, do you got some answers, some questions to Frank?
No, it was quite a nice idea to use the trees and the proper order of searching, going through the tree.
Yeah, what I searched for while implementing the solution in the morning was a dynamic programming solution. And I was fairly sure that it somehow exists, so we can create a table of best outcome of Ori and then make this the best outcome of Clay, and then from that calculate the best outcome of the result or something like this. But it turned out there was no such solution, and I hunted like a phantom for like some hours. Yeah, well,
Okay.
at some point Achim and I decided to read in the Reddit how it really works, and then what's not so difficult. Yeah.
Okay, nice. So then, thank you, Frank. Thank you, Maciek. And we see us tomorrow, 6 o'clock. Bye-bye.
Thank you. Goodbye.